we were talking about pizza and how the recipe gives us relationships between the amounts of the ingredients and the amounts of pizza. So let's look at that recipe again. And now, what if we have available 4 crusts, 10 cups of cheese, and 15 ounces of tomato sauce? How many pizzas can we make? I have 2. I've got 5. I've got 3. So what are we thinking about here?
The amount of each thing, like the amount it takes in.
Yeah, so what we have to do is we have to look at each of these ingredients and see how many pizzas could I make with that much. So with 4 crusts, we could make 4 pizzas, right? And then the others are not quite as obvious, but 10 cups of cheese, there's 2 cups per pizza, so that would be 5, right? And then here's 15 ounces. We need 5 ounces for each pizza. So we can write that out. Started to write a 1. I made it into a 4. So we've got 4 crusts, and we've got 5 ounces of sauce, and we have 10 cups of cheese. And what we're doing in our heads is we're figuring out how many pizzas can I make with each of those things, right? So our recipe tells us that we need 1 crust for every pizza, 1 crust per 1 pizza. And so with the 4 crusts, we could possibly make 4 pizzas. That one we didn't really have to think about too much. Then there's the sauce. Well, again, we're looking at the recipe. And the recipe says for 1 pizza, I need 5 ounces of sauce. 1 pizza, 5 ounces of sauce. So there, putting the units in and converting the units using dimensional analysis takes away the question, should I multiply 15 by 5 or should I divide 15 by 5, right? So that's going to give us 3 pizzas. And then the cheese, we did this one on Tuesday. 1 pizza requires 2 cups of cheese. So that would be, that looked like it was going to be cups of cheese, but it's actually pizzas. 5 pizzas. So we can make 3 pizzas. We can't make 4 plus 3 plus 5 pizzas, right? Students do that when we get into the stoichiometry. They add the numbers together. And you kind of giggle about that with this example. It's like, no, that's ridiculous. Well, yeah, it is. You can see it with pizzas, and you can't see it with grams of hydrogen, right? So we can imagine what's happening here, right? We're making pizzas. We make 1 pizza. We make 2 pizzas. We make 3 pizzas. When we hit 3 pizzas, we're out of sauce. We're done making pizza. Now, you could improvise and maybe make some cheesy bread or something, but you can't make any more pizza because you don't have any sauce. So it stops. What happens to the crust and the cheese that's left over? They're going to sit there on the counter. Maybe you'll put them away for later, feed them to the dog, or do something, but they're extras. Okay? Here's the same idea in pictures. 4 crusts, you can make 4 pizzas. 10 cups of cheese, you can make 5 pizzas. 15 ounces of tomato sauce, we can make 3 pizzas. What we're doing is we're looking at the number of pizzas and we're finding the smallest number. Because when we get to the smallest number, that means we ran out of something, production stops. And so whatever we run out of is our limiting reactant, because it limits how much stuff we can make. If we had more of this, we could make another pizza, but we don't. so we can't. So this is the limiting reactant, and the least amount of product, that would be considered the yield. How many pizzas did you get? Any questions yet? So tomato sauce is a limiting reactant, the reactant that makes the least amount of product. The maximum number of pizzas we can make is that smallest number from our little calculation. That's called the theoretical yield. So that's in a chemical reaction, that's the amount of product you can make based on the amount of the limiting reactant. The ingredient that makes the least amount of pizza, limiting reactant, determines how many pizzas you can make, the theoretical yield. So, in reactions that have multiple reactants, reactions that have multiple reactants, which is most of them, it's very likely that one of the reactants is going to get used up before the others do, which is a lot like baking at home. If you go home and you're going to make a batch of chocolate chip cookies, are you going to run out of everything at the same time? No, I've never had that happen, and I've made a lot of cookies, right? You usually run out of something like the chocolate chips or the butter or maybe the eggs, but like the flour and the sugar, you usually got lots of those. So we almost never have just the right ingredients of all of them to make a set amount. Usually there's one that's present in lesser amount, and that's the limiting reactant. So the limiting reactant gets completely used up, and everything else, all the other reactants that there are left over, are said to be in excess, because there's excess or extra of them. So the theoretical yield is how much we could make if everything goes perfectly. Does everything always go perfectly when you make pizza? No. Maybe you got distracted while you're baking one of them, watching cat videos on YouTube or something, right? And you didn't hear the timer, and then you didn't hear the smoke alarm, right? And you burned it. So you only end up with 2 pizzas. Or you dropped one on the floor and the dog got it, right? So you had enough stuff to make 3 pizzas, but you only made 2 because things happen. So the actual yield is how much you actually make. And then what we call the percent yield expresses the efficiency of how much stuff we make. So that's going to be the actual yield divided by the theoretical yield times 100. If everything goes perfectly, if we didn't mess up at all, we'll get 3 pizzas, and we should have gotten 3 pizzas, 100% yield, perfect, gold star for you. Oftentimes that doesn't happen. So this slide is just a summary of all those terms, which this is one that, could be helpful. You can go find all of these slides on Canvas, pull them up on your phone, and then just screenshot them, and you'll have a really nice, clear picture, and then you could file those away in an album of, chemistry nerd pictures that you might want to look at when you're stuck on your homework or something. So let's apply these ideas to a chemical reaction. So we talked about methane reacting with oxygen to form carbon dioxide and water. This equation is telling us that 1 molecule of CH4 reacts with 2 molecules of O2. Well, what if we have 5 molecules of CH4 and 8 molecules of O2? What are we going to run out of first? Well, the best way to solve that is to do a little calculation, right? If I have 5 methane molecules, I'm going to get 1 CO2 for each CH4 that I use. So I'm going to end up with 5 CO2 molecules. This is just like what we did with the crests. Okay? And then the 8 oxygens, the chemical equation tells me I need 2 oxygens for every carbon dioxide. So 2 oxygens for every carbon dioxide. This could make 4 carbon dioxides if I use up all the oxygens, right? So 4 carbon dioxides is smaller than 5. So that's our limiting reactant. So the O2 produced the least amount of products. That's the limiting reactant. The other reactant is in excess, and this smallest amount is the theoretical yield. So let's look at this and see if we understand that. Nitrogen and hydrogen gas react to form ammonia according to this reaction. A flask contains a mixture of reactants represented by the image shown at the left. Which of the following images best represents the mixture in the flask after the reactants have reacted as completely as possible? What is the limiting reactant? Which reactant is in excess? So some students find a problem like this hard because they learned how to do the calculation, but then when you just have to stop and think about it, you're like, ah. But then students who find the calculations hard can find this a little easier because we took the math out of it mostly. So this is telling me that each nitrogen reacts with 3 hydrogens. So what if we group these guys, right? So there's a nitrogen and 3 hydrogens, and that's going to make 2 of the NH3s, right? Everybody okay with that? I have a nitrogen, another one over here, and that one can react with 3 of these remaining hydrogens to also make 2 ammonia molecules. And what do I have left? I have those 3, two hydrogen molecules left over. So what's the reactant that got used up? The nitrogen. So the limiting reactant is the nitrogen. Which one is in excess? The hydrogen. Which flask, A, B, or C, represents what's left after the reaction occurs? C. Here I've got 2 ammonias and another 2. So those are the ones that got made by using these guys up. And then I have those leftover 2 hydrogen molecules. And they're just going to hang around. Any questions? Yeah.
Do you just want to think about it like how you say, like you start with like a mass, and you'll have like an original mass later, so all the particles will still have to be there, or atoms?
Yeah, really. Yeah, in essence, because when we do calculations, a lot of times we're not paying attention to how much excess is left. But if we're looking at mass balance, the law of conservation of mass, then when we look at the products, well, it's the product that was formed, but we also have the unreacted reactant that was present at the beginning also. And so total reactants has to equal total products. Great question. Anybody else? So that's looking at it in moles or molecules. Of course, we measure things in masses, right? So this is a strategy for finding the theoretical yield given a limiting reactant problem. So this is how your book shows to do it, and there's nothing wrong with this. It's just not my preferred method. So you take the one reactant and you figure out how many moles of product that would make. You take the other reactant, you figure out how many moles of product that would make, and you choose whichever one is smaller, and the smaller one you convert to grams of product for your final answer. I prefer to do this. Let's just go all the way to grams of magnesium oxide for both of them. and then pick the smaller number. So we're going to do grams to moles to moles to grams on each of the reactants, and we're going to look at the answer and pick the smallest number. I think conceptually it's simpler than stopping at moles and then tacking on this one thing at the end. Let's do an example. A reaction mixture contains 42.5 grams of magnesium and 33.8 grams of oxygen. What is the limiting reactant and theoretical yield? Suppose that the actual yield is 55.9 grams. What is the percent yield? Well, things just got real here, right? This is serious chemistry going on. So we've got our masses. We got 3 numbers, right? So we want to pay attention to those. And then we have our questions. We want to know what is the limiting reactant. We want the theoretical yield and the percent yield. Nothing like starting out small. Just going to go for all of it at once. Use the chemical equation to organize these masses, right? So grams of mg is also megagrams. Megagrams, magnesium. 42.5 grams of magnesium. And 33.8 grams of oxygen. And they're asking, what's the theoretical yield? Well, I only have one product here, so they're asking me, how much of that could I make? So, question mark, grams. Well, what about that number? Isn't that the theoretical yield? It's the actual yield. It actually says it's the actual yield. It says the actual yield is, right? So this one's really clear. It doesn't always say it that clearly. This is the actual yield. When this reaction happened, one of the pizzas got burned, right? So not all of the stuff got made. There's like tons and tons of reasons that happens, but we don't need to know about that. So this is how much actually got made, and in a problem like this, they have to tell you what that is. If you're doing an experiment, like we did on Tuesday with the copper, then you're actually going to be measuring your actual yield, right? And so you find it out that way. But if it's in the book, on a test, on a worksheet, they have to tell it to you. Okay, so what is the path for stoichiometry? Grams to moles to moles to grams. Grams to moles to moles to grams. That's always a good place to start. So I have 2 masses for my 2 ingredients. That's what tells me this is a limiting reactant problem. I need to do 2 calculations. So I'm going to go grams to moles to moles to grams for each of them. So 42.5 grams of magnesium. And that's going to go to moles of magnesium. And then moles of my product, magnesium oxide. And then to grams of magnesium oxide. Grams to moles to grams. Yep. And then this is the same idea that we've been working with since the first day. Well, maybe it wasn't the first day, but since chapter 1. I'm going to put this unit in the denominator of the next term so that they're going to cancel out. After I get all of the units in, then I put numbers in. This mole ratio, moles to moles, comes from what's in the balanced chemical equation. So 2 moles of magnesium make 2 moles of magnesium oxide. So there's a 2 in front of moles of magnesium and a 2 in front of moles of magnesium oxide. relationship between grams and moles is given by the molar mass. Okay. This first one is an element, so we just have to read it off the periodic table. 24.31 grams for every 1 mole of magnesium. But then for the product there, we need to calculate what its mass is. There's 1 magnesium and 1 oxygen. I don't really trust myself. I should be able to do that. I did it right. Always good to check with your calculator. So 1 mole of magnesium oxide is 40.31 grams. And now we're going to start at the left and move to the right, multiply by the top of the fraction and divide by the bottom of the fraction. So 42.5 divided by 24.31 times 2 divided by 2 times 40.31 equals. How many sig figs did I start with? 3. So even if none of the rules of sig figs stuck in your head, what would be a good guess for the answer to have? 3. And it's correct this time. It's correct a lot of times. So there's my 3. I'm going to write down 2 digits extra because I said you should. So there, that's how much magnesium oxide could be made from that much magnesium. Now we're going to do another calculation. I'm going to change color because it gets a little busy in here. So 33.8 grams of oxygen. Grams to moles to moles to grams. So I'm going to go to moles of oxygen. And then I'm going to moles of magnesium oxide. And then I'm going to grams of magnesium oxide. We want to end up with the same quantity. You know, we don't want to end up with grams of oxygen at the end or grams of magnesium. We want to end up with grams of the product, magnesium oxide, so that we can compare the two and see which is smaller. They're having fun in Chem 3A lab today. Very excitable, that guy. You're stuck with me. I'm told I have a dry sense of humor. Okay, all the units. Numbers. The moles in the middle are the easiest because they're just sitting up here waiting for you to pluck them, right? So what's in front of the O2? An implied 1, right? If it was 0, there'd be no O2. And in front of 2 MgO, well, in front of 2 MgO, there's nothing. It is 2 MgO. And then here we've got for oxygen, that's one of those diatomic elements. So its mass is 32.00. And then look at this last term. Grams of magnesium oxide per mole of magnesium oxide. That one is going to be the exact same term for both of our calculations. Which is kind of why I don't see the point in stopping here and then just taking one of those forward. It's just really not much work to just do it for both of them. 33.8 divided by 32 times 2 times 40.31. 85.155. So again, we should have 3 sig figs because we started with 3. This is the hard part. What's smaller, 70 or 85? 70. So we're picking the smaller answer. Okay, that is our theoretical yield. We can't make more than that because at that point we've run out of what? We ran out of magnesium. You run out of magnesium, you can't make any more magnesium oxide. This is the limiting reactant. That guy right there. He's really going at it today. To report the answer here, we would want to round it to the correct sig figs. And so that would be 70.5 grams because the next digit is 7, so we have to round the 4 up to a 5. So that's our answer for theoretical yield. Okay, so we took care of limiting reactant, and we took care of theoretical yield. Now we need the percent yield. There's an equation for percent yield. Percent yield is equal to the actual yield divided by the theoretical yield. I just call him Theo because his name's too long. So, what's the actual yield? The actual yield is 55.9 grams. I mean, you can't get too much clearer than that. 55.9 grams. What's the theoretical yield? We just calculated it. So this was a rounded number for a final answer, but now we see it's helpful to have those 2 extra digits because when we're continuing our calculation, we shouldn't use a rounded number. My open math with your lab reports gets really picky about that. So I'm going to put 70.472 grams down here. We'll multiply by 100. And 79.322%. Is again, I'm carrying on that habit of, as I write down the answer, I'm going to underline the last sig fig, and then I'm going to write 2 more digits. And then I'm going to round and say the percent yield is 79.3%. We've got pi, tie, and ver. Any questions? The book really likes limiting reactant problems. These are going to come up in several chapters. Okay, let's do another one. Ammonia can be synthesized by this reaction. What is the theoretical yield of ammonia in kilograms that we can synthesize from 5.22 kilograms of hydrogen and 31.5 kilograms of nitrogen? Read the problem all the way through. Highlight the numbers. Identify what you're trying to find. Ammonia in kilograms. Now I'm going to take those numbers and write them under the chemical equation. So 5.22, well, that's maybe a little too big. Needs to fit. 5.22 kilograms of that and 31.5 kilograms of that. And then I want to find how much ammonia in kilograms. I have 2 reactant masses. I'm going to do 2 grams to moles to grams. One with the first one, one with the second one. Grams to moles to moles to grams. What's our problem? Are we starting with grams? No, we're starting with kilograms. Well, we could add that onto the beginning, right? And we're supposed to get to kilograms. Well, we could add that onto the end. I don't know if you remember, but we did a problem like this on Tuesday. And we wrote out all the terms, and then we saw that we were multiplying by 1,000 and dividing by 1,000, and those canceled each other out. So I'm going to show you two other ways to think about this, and you pick what makes the most sense to you. If you want to write them all out, do it. If that makes the most sense to you, that's what's going to get you correct answers. Some of you are really just not into writing stuff at all, so I'm going to show you how you can make it a little shorter. Okay, so 5.22, and what I'm going to do here is I'm going to write the kilo in a different color because kilograms is like 1,000 times grams, right? So what I'm going to do is I'm going to cancel out the grams. I'm not going to cancel the kilo. I'm just going to leave it sitting there. And when we get to the end, we'll bring it over. So we're ignoring the red for right now. So, grams, kilograms of what? Kilograms of hydrogen. So grams to moles to moles of ammonia, because that's what they're asking us about, to grams of ammonia. But they asked for kilograms. Just wait. So grams H2. The grams H2 cancels out. The kilo doesn't cancel out. This method is not for everybody. Moles H2O. Moles NH3. The mole ratio I need, 3 moles of hydrogen, 3 moles of hydrogen, and 2 moles of ammonia. That comes from this one right here. I need the molar mass of hydrogen, 2 times 1.008, 2.016. And then at the end, I need the molar mass of ammonia, which is 1 nitrogen and 3 hydrogens, 17.034. Okay, let's take our numbers. 5.22 divided by 2.016 times 2 divided by 3 times 17.034 equals. This is going to have 3 sig figs because I started with 3. The mole ratios are exact. My molar masses should not be smaller than 4 sig figs. That kilo is still sitting there. So that didn't cancel out. It's still there. Kilograms of ammonia. Anybody like that method?
Yeah.
Yeah? Anybody not like that method? You just don't want to say it. I'm going to show you one other way. This is kind of a compromise method. Some people are like, that it's a little too fancy for me. Just let's keep it more basic. Okay, we can do that. But this will still be a little bit shorter. So we're going to do a very similar calculation with the nitrogen. 31.5 kilograms of nitrogen. Well, there we go. What does kilo stand for? times 10 to the 3. So what if instead of writing kilo, I write times 10 to the 3? That means the same amount of stuff. That number is not in proper scientific notation, but this isn't the final answer, so I don't care, and your calculator never cares. So there's grams of nitrogen. We're going to go to moles of nitrogen, to moles of ammonia, to grams of ammonia. Moles of ammonia down here. Those are going to cancel. Moles of nitrogen down here. Those are going to cancel. Grams of nitrogen down here. Those are going to cancel. I'm not quite done because I got to grams. But I need to go to kilograms. So I need to add one more term in there, kilograms. Right? Kilo stands for 10 to the 3. 1 kilogram is 1 times 10 to the 3 grams. I didn't even think of this until just now. If you write it out that way, you could just cancel out the 10 to the 3s, or we can leave them there. It's up to you. We need the molar mass of nitrogen. .02. And we've got 2 moles of ammonia for 1 mole of nitrogen. So this one's 2 to 1. The molar mass of ammonia has not changed in the last 10 minutes, so we can just copy that down. And cancel the grams. So 31.5 EE3 divided by 28.02 times 2 times 17.034 divided by 1 EE3 equals. Anybody else get that number? I think it's right. It just looks funny to me for some reason. Okay, what's smaller, 29 or 38? 29. Let's see. So this is the smaller number. So that means my theoretical yield is 29.4 kilograms of ammonia. As I'm rounding this, the next digit is 0, so I round down. If everything went perfectly and all of the hydrogen got used up, you could make 29.4 kilograms of ammonia. Is it going to happen perfectly? No, nothing ever happens perfectly. Any questions? Yeah.
So we'll just do, once we do like one part of it, we're gonna just do the second part, and it doesn't matter which way we do it, between like the,
Well, like you mean like if you wanted to do nitrogen first and then hydrogen?
that, yeah, or when you're talking about like the kilograms of leaving it in, or.
Oh, yeah. Yeah, it doesn't matter. And you can do the method I showed on Tuesday also, where you put in both of the terms in the beginning and the end. And then there's also some people that they're going to convert the kilograms to grams, write that down. And now they're going to do grams to moles to grams, and they're going to take that answer and convert to kilograms. You know, our minds work in different ways, and so whatever makes the most sense to you is good. Any other questions? $29.4. Mining companies use this reaction to obtain iron from iron ore. reaction of 167 grams of Fe2O3 with 85.8 grams of CO produces 72.3 grams Fe. Determine the limiting reactant, theoretical yield, and percent yield. This is sounding a little bit like that first one. Read the problem, highlight the numbers, highlight the questions. We want limiting reactant, theoretical yield, and percent yield. I'm going to put my numbers under those formulas in the balanced chemical equation. So I have 167 grams of that. I have 85.8 grams of carbon monoxide. And this is saying 72.3 grams of iron. I'm supposed to find the limiting reactant and the theoretical yield. I can't really find the limiting reactant until I find the theoretical yield, because I have to find out which one gets used up. So I need to find the theoretical yield. Well, this one has two products, right? Which product are we interested in here? The iron or the carbon dioxide? Companies use this reaction to obtain iron. And this is telling us that it produced this much iron. So we're interested in the iron. We're going to ignore the CO2. That just floated away into the atmosphere. And yes, the environmentalists are going to be very concerned about the CO2, carbon footprint, right? But this is chemistry. Well, is this the theoretical yield then? 72.3? I wrote that under there. That'd be too easy, wouldn't it? What have we been doing? We've been doing two calculations and picking the smaller number. And then let's think, well, percent yield, what do I need to calculate percent yield? I need an actual yield and a theoretical yield. I calculate the theoretical yields using stoichiometry. I can't just calculate the actual yield. This is the actual yield. They just didn't come out and say this is the actual yield. They said this reaction produces this amount. When she made pizza the other day, she made 2 pizzas. There were supposed to be 3. Something happened. So I don't want that to be down there. So I'm going to move it. So I'm going to stick it up there, and I'm going to label that. This is the actual yield. So I want to calculate the theoretical yield of iron. So grams to moles to moles to grams, and grams to moles to moles to grams. 167 grams of Fe2O3. I'm going to convert that to moles of Fe2O3. And I'm going to convert that to moles of what the problem is interested in, which is the iron. And then I'm going to go to grams of iron. I'm going to put the rest of my units in so they cancel out the way they're supposed to. Mole ratio, 1 mole of Fe2O3 to 2 moles of Fe. 1 mole of Fe2O3, 2 moles of Fe. Molar mass of iron is just sitting up there on the periodic table, but for the Fe2O3 I have to calculate it, 55.85 plus 3 times 16. 159.7. It's another example of them giving us 3 sig figs. We're going to end up with 3 sig figs at the end. 167 divided by 159.7 times 2 times 55.85 equals 116.81 grams of iron. Now we're going to do it again. It's almost exactly the same. 85.8 grams of carbon monoxide. We're going to convert that to moles of carbon monoxide, and then to moles of iron, and then to grams of iron. Mole ratio, 3 moles of CO to 2 moles of Fe. 3 moles of CO, 2 moles of Fe. At the end, this mass is the same as the other one. And then I have to calculate the mass of carbon monoxide. .8 plus 28, nope, no pluses, divide by 28.01 times 2 divided by 3 times 55.85. $114.05. What is my theoretical yield? 114. That's the smaller number. So my theoretical yield, rounded to the correct number of sig figs, is 114 grams of iron. What's the limiting reactant? This is the theoretical yield. The starting one is what got all used up. That's my limiting reactant. And then I'm supposed to calculate the percent yield. So this is the actual yield, which is this guy up here, 72.3 grams, divided by the theoretical. I'm going to use the unrounded value because that's what I do. 72.3 divided by 114.05 times 100. 63.393%. 63.4%. Percent yield. Any questions? Students sometimes tell me, well, it looked so easy when you did it in class.
Mm-hmm.
Well, it looks so easy because I've been doing this over and over and over again since before you were born, right? I've had a lot of practice. It's not going to be easy the first time you try. But you're going to have to make mistakes and figure them out and try again and make mistakes and try again, and it will get easier and easier. You had a question?
I just lost it.
Oh, sorry. Anybody else? Questions? Stoichiometry problems, grams to moles to grams, really important part of chemistry. Limiting reactant problems will come up a lot But really, all they are is do stoichiometry twice and choose the smaller number.